Hi there. So, as promised, this is going to be a recording of me trying out the Fall 24 61A second midterm. So, I think staff should have an official walkthrough for these problems coming out soon. But I guess how this differs is this is going to be me trying out these problems for the first time. So, instead of me sort of knowing what the solution is and explaining to you why the solution is what it is, this is more so of just like stream of consciousness of what I'm thinking about as I'm going through these problems. Maybe it's helpful, maybe it's not, but if it's helpful to one person, then fantastic. So let's start, and yeah, hopefully I don't do too bad because that'll be a little embarrassing. So let's begin. Um, and just again, as a disclaimer, this isn't going to be the most coherent explanation of these problems, but more so just things I notice or things I use to potentially help me solve the problems. So yeah, here we go. Um, we start off with what would Python do? Um, let's make an environment diagram. Um, all right. So it seems like we're gonna have a bunch of trees in a dictionary. Crow and scare are our trees. And then we're going to have two functions. All right, let's start with drawing out our trees. So I have scare. Scare is going to be a tree with rooted at 0 with branches. It has 3 branches. So it's going to have 3 branches. The first branch is rooted at 4. The second branch has a label of 5, and the last branch is rooted at 2. The middle branch also has its own branch with just the label 10. So there's scare, and we're also going to want to have crow. Crow is the tree rooted at 9, and its branches are 1, 2. The second branch is going to be rooted at 7 with a single child, 6. And then the first branch is going to be the tree that is scare. So branches is a list of trees. So we're saying for that tree, we want an existing tree. So this will look something along the lines of this, I think. Okay, so first tree, 3 branches. All of them are just leaves except the middle one, 5, 10. And then second tree has just 2 branches. First one is to scare, and second one is 7, 6. Okay, let's move on. So it's going to ask us for crow dot branches of 0 dot label. Okay, so who is crow? Crow is right here. Who are its branches? Branches are right here. Branches of 0 is going to be the first branch. Go to the pointer. That brings me over here. Get the label of whatever tree this produces. So this is going to evaluate to scare. So if I do scare dot label, that will be 0. I will now call hide on B for B and scare dot branches. Okay, we are now looking at scare. Scare is going to be all of these trees. And for each of these trees, I'm going to call hide on it. Hide is a function that, okay, thankfully they didn't make it too hard. I simply want the label. So for each of these trees, I will collect their labels and put them in a list. So the output, I believe, should be 4, 5, and 2. I will now call climb on the crow tree using the hide function. Let's look at climb. Climb is a function that takes a tree and a function, it seems. That function will be used here. It seems like the function has no other usage except to be passed in as a key. So here we have a recursive call, and f is just going to get passed along infinitely. So f does nothing else. It's just a key. Cool. Good to know. What else? So right now what I'm thinking about is trying to figure out how this function is used before or I'm thinking about what is the purpose of this function before I try to go ahead and solve whatever this is. So what is the purpose of this function? So this says if the input is a single leaf, I shall simply return 1. And then if it's not a leaf, what I'm going to do is, so I start here, I say, am I a leaf? I'm not a leaf. So I will return my label, which is 1. And then I'm going to iterate across my branches, 1, 2. For each of those branches, I'm going to apply the key function. Okay. It's a little hard. Okay, let's break this down more. So the first thing that needs to happen is this, right? Before I can call climb, I need to know what I'm calling climb on. And so let's first think about what this returns. This says across all my branches, I'm going to return the tree that produces the max something. And that something is going to go off of whatever key we pass in. And the key is going to be F. And if we pass in hide, hide simply gets all the labels. So I'm saying across all of my subtrees, hand me back the branch that has the greatest root value. Not the greatest label overall, but just the greatest root value, because if I call hide on each of these, that will produce 2 and this will produce 3. So I'm going to go ahead and select this branch. And then I will recurse on this branch. And then now, when I recurse on this branch, it's a leaf. So I will hit the base case and I'll hit this. So therefore, the output is 1, 3. So what have we done? So we've seen problems before where we return labels as a list. And these sort of are path problems. So this climb seems to be returning some sort of path from the root down. And at every step along the way, it's going to take it's just going to take the largest so it's gonna make a path, and every successive node is gonna be the largest one possible. So it's gonna go along like a max increasing path, sort of, or not necessarily increasing, but just a max path by some definition. Okay, so now that I know what it does, I can go back and solve the problem much more easily. It tells me to look at the crow tree, and for this, now that we know what it does, I will start at the root, and I'll just snake along depending on which of my children have a larger root value. So here it's going to be 0 versus 7. So it should be 7. And then from the perspective of this tree, it's going to be nothing versus, what's this? The 6 or 0? That's a 6. It's going to be nothing versus 6, and 6 is larger. So the path produced is 976. Okay. I will now do the same thing with climb, but my max function is different. So before I was choosing my next, along every fork, the path that I'm choosing is going to be the one that has a larger label. Now the key we're going to apply is run. What does run do? So same approach here. I'm going to try to figure out what this function is ultimately doing on a simpler input. So let's say I had this tree and I call run on it. It is not a leaf, so I will not return a label. I notice that this is not a list, so this shouldn't be a path. Then I'm gonna go max map of run t dot branches. Okay, let's do this step by step. Let's first do here, max map run onto t dot branches. So I'm gonna map my own function onto my branches. Interesting. Why do we need to do that? It's not apparent to me why we need map over list comprehension, but I think they're the same thing. So for each of my branches, I'm going to recurse map on it. So let's recurse run, or I'm going to recurse run on it. So when I recurse run on this subtree, it's again not a leaf. So I'm going to recurse on this subtree, which is 4, and it's going to produce a leaf. So this is going to return 4. And then I will backtrack up to my other subtree being 3. And it is a leaf, so I will return t.label, which is 3. And then finally, I will take the max of these. You see. Okay, so my claim is because the only time this function ever actually returns is when we hit a leaf, right? The only possible values this run function can produce are leaves. And then we're going to take the max over the possible values my function produces, which is just leaves. So I'm taking a max leaf of my tree is, I believe, what this function is doing. And this will only ever return a singular value. Yes. So it will return the max leaf in my tree. Okay. So now let's call climb with this max leaf function. So again, we ask, hey, before I call climb, let's figure out what this line is doing. So I'm going to say across all of my branches, I'm going to for each branch, I'm going to call run on it, and that is going to produce the max leaf. That is going to produce the max leaf. And then we're going to take the max of those leaves. So it seems like, or not, we're not going to produce the max leaf because again, we're taking a max function, which returns to you the item that produces the max value. So I don't care about the max value, which is the max leaf. I care about the item that produced the max leaf. So ultimately, max is going to return one of these trees. And again, climb generates a path which chooses the next item based on whichever f you pass in. So now I'm going to make a path such that the next item that I include on my path is the one that has the next item I include on my path is the item in a subtree that has the largest leaf. So I'm going to look at my two options. I'm going to say which one has the larger leaf, and I'm going to snake down that path. Okay. So let's try to do that for crow. So we are at crow. I will ask, hey, of my subtrees, this is one subtree and this is the other subtree, which one has a larger leaf? It will be 10. So I will come down, step in along this path, and I will iteratively produce my path. So let's just get started here. I start at the root, and then the next step I take is 0 because I'm going to step into the subtree with the larger leaf, and I'm going to look at all of these, find the largest leaf, and of course it's still the same subtree. So basically, I'm just going to step down this path. Okay, so let's see. So ultimately, what we have done here is I've traced down the path that brings me to the largest leap. Cool, cool function. So 9, 0, 5, 10 is that path. All right, I hope we are done with this tree. And now I have to do jump of 13. So I'm indexing into a dictionary here. Okay. So let's figure out what this dictionary is. I'm going to say for x in the range 50. So okay, I'm going to say for the range from 1 to 2 to 49. That's not 49. I'm going to do for each of these values, I'm going to perform some computation on it. And that computation is this thing. So for each of these values, I'm going to generate I'm going to generate this. This is a dictionary comprehension. You learned dictionary comprehension in this class? Okay. So it's a dictionary comprehension. So like in a normal list comprehension, this might just be like f of x or something, right? But in a dictionary comprehension, you have to add a colon because every entry in a dictionary is going to be key value binding. So the key value binding that we're going to produce for each x is this binding where this is the key and this is the value. And these are all my x's, right? So here my x is simply 1. And the key that binds to 1 is 2x minus 1. So if I pass 1 into this function, 2 times 2 minus 1 will be 1. Same thing here. Well, x is simply whatever this value was. And then that's the value. And then the key is going to be 2x minus 1 is 3, and so on. Okay, and so we produce a dictionary that looks like this. We don't actually need these parentheses. Okay, so this dictionary is a little weird because the value is like the key that produced the value. Like, okay, I don't think that makes sense. Let's move on. So let us start inside out by the evaluation order. So let's start with jump of 13. So I'm going to look in my dictionary. I'm going to find the key that corresponds to 13. So the claim is that there is some 2x minus 1 pairing where 2x minus 1 is 13. And then I have to figure out what is the corresponding value that that key corresponds to, but because of how we created our dictionary, the value produced by the key is the same thing as asking what is the x. This value is equivalent to saying, hey, what is the x that when I feed it through 2x minus 1 produce 13? So this might simply be an algebra problem, I think. I don't know why it says 1 here. Right. So what is the x such that when I feed it into this, I get 13? So this is algebra. Wow. It's algebra. So x will be 7. Let's see. Does this check out? Does this satisfy our equation? So if x is 7, then 14 minus 1 is 13. All right. So jump of 13 is 7. And now that we've sort of got down the algorithm for this, so jump is a dictionary such that if I want to find the value for a given key, I just have to find the x that satisfies 2x minus 1 equals the key. Number 2, full disclosure. I helped review this problem before the exam, so I have done this before. Yeah, but this is the only one I've done this exam. Pizza by the slice. So another environment diagram problem. It seems in the global frame, I'm going to have my slice up function, and I'm going to have a list. That list is bound to 3, 4, 5. I will now print slice up of t, and number 1 is going to be asking us what this produces. So we have to call slice up, open up that frame. First thing in my frame will always be whatever the parameter is. So that should be S, and I'm feeding in the value for t. So in the context of the global frame, t is this list. I'm going to point my parameter S to that t. To step into the function, first thing I see is copy. Copy, I'm going to point at whatever S is pointing at, because S is an object. So we're not going to, or assignment of objects is simply redirecting a pointer. Then I'm going to set t is equal to copy. So let's make this first before I try to point t at it. So if I put copy in a list, okay, if this wasn't copy, like if this was t is equal to 3, then we would have something like this, and then point t to it. But the item is not a list. The item is instead a list itself. Or sorry, the item is not a primitive. Instead, the item is an object. And when the item is object, we will always point to it. All right, interesting. So I have a bunch of things that point to this list. And now we're going to do stuff to it. So while the length of my list is 1, so right now my len is equal to 3. So while my length is not 1, I'm going to, seems to be iteratively pop from it. But first we have to do this thing. I'm going to do t.append s of 0 to len of s minus 1. Okay, so if this was 0 to len of s, this would do nothing. This would simply be the whole list, right? If I go from 0 all the way up to the end. But because I have the minus 1, that means I'm going to go from 0 all the way up until the last item, or not including the last item. So this is a slice that will always make a fresh copy of every item except the last one. And at each step, I'm going to add that fresh copy of a list, because slicing always produces a new copy, and I'm going to add it onto the end of t. So iteration 1, I'm going to add onto the end of t. Appending will always just give me a single box, right? Extend might give me multiple, but I know append will always be a single box. I am adding a list, which means I'll add a pointer to, again, as I said, a fresh copy of S of this, which will be a copy of every item of whatever S is up until the end. So I'm going to have to make a new list somewhere in my environment, and I will point to it. I will do s.pop. I don't do anything with the return value, so we can move on. And finally, I'm going to set s of 0, which is over here, to the new length of s. And because my list has been mutated, the new length is 2. So the first item there is now 2. Now I'm done with my first iteration. My length is 2, which is still greater than 1. So I will enter the next iteration. I will again append on something. I'm going to append everything up until the last item of my t list, which is now shorter. the items in my T list are now 2 and 4. So, or no, I have to cut off the last item. So simply just 2. I go back here, I'm going to pop off the last item, and I'm going to set s sub 0. Well, now the length is 1. So I'm going to set this to 1. And now since my length is 1, the loop will quit and I will return t. So I will return whatever t points at, being this list that we've made. And finally, I will print that return value. So it's asking me, hey, can you print this thing for me? And this thing is simply the list where the first element is yet another list. So I'm going to nest it. What is in that list? It's this one value up here because s sub 0, we kept replacing with the length. The loop stopped when the length is 1. So the item that replaced it will be 1. The next item is yet another list. So I'm going to nest it again. We have 3 and 4 in here. The next item is a list. So we're going to nest a 2. B, what would be printed by the expression print of t on line 12? So now I want to print t. What is t? T is this absolute mess over here. If I remember correctly, we popped off these items. So t is simply a single element list. And this was the length. So it will just be 1. That's when the loop stops. What is the order of growth of the time it takes to evaluate list of q, where q is a list of numbers. Creating a list takes one element. With one element takes constant time. Making a copy of a list takes linear time. Okay. So list of q is O of len of q. And list of q produces yet another len q list. Okay, so if I call list on this whole thing, this is another O of len of q operation because the length has not changed, right? Here, the length was q. Here, the length is still q. So I'm doing 2 independent O of len q operations. So this will be O of 2 of len q, which is just linear with respect to the length of the list. Length of the list is my len q, and it's going to take O, so len n is equal to len q. Then my big O is simply 2n, which is O there. All right. Let's do number 3. 61A software store. A store instance has a list of branches, and each branch is also a store instance. Is this not just a tree? Oh, it is a tree. Okay, forming a tree of stores. Each store instance also has a list of programs called its inventory. And for a given store, we have 2 methods. We have the copy method, and we have the add to method. And then it seems like this question just wants us to implement those 2. Okay. I need to implement this and this. Copy will return the number of times S appears in the inventories of all nodes in its tree of stores. What is S? Copies of S returns a number of time S string. Okay, so S is a string, appears in inventories of this tree. And add to returns a function that takes the string and appends it to the inventory of its kth branch. Returns a function. Interesting. Add to seems a little tricky to me. Let's work on copies first. So I will return the number of times this S appears in all inventories of this tree. So let's first try to understand this tree structure. Like I have a store. And what is this? So right now I'm just trying to think about how I can make sense of what this store object is. Okay, I should probably look at the init here. And it has branches, which makes this a tree, and it has an inventory. So what I'm thinking about now is this really reminds me of a normal tree, but instead of self.label, I have self.inventory. So my claim is that how I'm going to conceptualize this tree is this is simply just our normal trees, but the label will instead be a list. Like this. Okay, and then each store has a list of programs of strings. So each of these is a program. They also tell us that each is a string, very helpful to know. And then the question they simply want us to answer is the number of times my S is going to appear in my tree. So let's say my input is S, or S is equal to X. All right. So if I want to count the total number of times that X appears in this tree, well, this is not much different from just counting the number of labels in a tree with the additional complexity that instead of matching my input S with every label, I have to check for membership of my input with respect to each of the inventories. So for every given label, I have to grab its inventory and then I have to say, hey, does this X exist within it? Oh, wait, no, that's not good enough because containership is just true or false. I need the number of times my S exists. So I will instead ask, okay, so that constrains me to have it to iterate through every single inventory. So for every single node, I have to grab its inventory and then I have to iterate through it somehow and then check if my S is equal to each item. All right. That is a good general idea of how this problem should be solved. Let's see what structure they give us. So they're gonna break this sum into two pieces, which makes sense to me. For a recursive problem. I noticed that the second option is for b and self-dot branches. So this must be the recursive case. And this must be the case where we're processing the node that I'm currently at. And this is saying all of the nodes below me. All right. So the nodes below me will simply be, well, actually, all right, let's start up here. Given a label, how do I count how many S's are in my label? Well, I have to grab my own inventory. Perfect. So, okay, this is exactly what we wanted. We said that we wanted to iterate through my inventory. So luckily we have a nice for loop here to help us out. So for every item in my inventory, if it's the case that, or for every item in inventory, if it's the case that I want to, that it's equal to my input S, and I want to produce some value, and because we're summing them, I know this has to be a number, right? So I know that P is a string, so it can not possibly be P. I would not want to sum over these strings, even though that wouldn't error. Len of self.inventory does not make any sense because we are not getting the number of items that are equal to S. We're just getting the count of all the inventories, which is not what we would want. Len of P is so P is the item itself, and the length of it tells us no information about equality with S. So by process of elimination, this has to be 1, but that also makes sense, right? We're filtering, we're sort of applying a equality mask on each item. If it's equal, produce a 1, sum over all of the ones that exist. So here, so this would produce a 1, and then neither of these will produce anything. So our final output is just a list of 1, and we sum over it, and that corresponds exactly to how many S's exist in this level. And then I have to also sum up all of these, the X's that might exist there. And that is very solvable for us, because I will take the recursive leap of faith and say, okay, I want the number of S's that exist in this subtree. How do I get the number of S's in a tree? I call myself on the tree. So B should simply be the recursive call, which is self.copies on each of my B's. And that is going to produce the count of all the X's in here. And then we're going to produce the count of all the X's in here. We're going to sum those up and add it onto however many we counted at this layer. For part C, I want to return a function that appends a string to the inventory of the branch at index k. Why do we need to return a function? I'm going to add to 1. Okay. So I don't think there's any real reason to make it a higher ordered function, but I guess it just allows this currying, so I can pass an input separately. So because I want to return a function, I'm going to start off here just by writing down lambda x. And this is a function that's going to perform a mutative operation. So what is x? Do I need an x? I'm not sure. I'll just leave it there for now. To the inventory of the branch at index k. So for a given store, let's say I come in here and I ask you to append onto the one store, so that would be here. And then I'm going to simply add the parameter they give us to this store. So again, it seems like we should be accessing the inventory of this subtree and adding on k to what it is. Or not k. It's not k, it's going to be the value. Okay, so that's what x is going to be. X must be this string right here. So I have a lambda function, and when this lambda function is called, it should take as input a item that can be appended, and I will do lambda x self dot branches. I'm going to get the kth branch, and I'm going to access its inventory because that is where my item wants to go. And then within that inventory, I will append on the item that the user wants to add. Interesting. All right. On to number 4. So mathy. So we have a proper divisor of an integer n is an integer d that is less than n that evenly divides into n. Okay. A semi-perfect number is a positive integer that is the sum of its proper divisors. So 24 is semi-perfect because you can decompose it as the sum of several numbers that are also themselves proper divisors. Therefore, it's semi-perfect. We cannot repeat numbers. Okay. Okay. So the ultimate question To determine whether a number is semi-perfect, the ultimate question we're asking is, given an integer n, can I decompose it as the sum of several values? And this reminds me of a lot of problems we've solved before, right? Partitions, count coins. In fact, let's reduce this to the count coins problem. To me, what I'm thinking about right now is this question simply appears to be sort of, can I make change for my input n? Can I make change for n using not my coins of $1, $5, $10, but using an alphabet of numbers of the proper divisors of n? Using proper divisors of n. So then to me, the approach for this problem should be, first I have to collect these divisors somehow. So the divisors of a given number n will be the k less than n such that n mod k is 0. So for all of these k's, these are my eligible coins that I will try to partition my n into. All right. So drawing from what I know from partitioning problems, one thing I noticed is that this is not counting partitions or anything of that nature. It's more so, is it partitionable? Is it partitionable? Okay, that's why we have all these return true and return false. So here we're saying my number is not partitionable. But first of all, I'm in a higher order function. So what is S and D? Drawing from partitioning problems, usually S and D are your N and your M, right? Where M is the value that I want to fit into the N. Here we're saying if the value that I'm trying to partition into my total is greater than the total, then return false. It's not possible. However, in which case should I return true? I'm thinking it's probably going to be one of these. Reason being, for this style of problem, I want to ultimately consider two choices. Right. So for each k in my k's, for a given k, I can either choose to include it as a piece of my summation of divisors, or I can choose to not include it in my summation of divisors. And the reason, right, I can either choose to include it or not include it, because the exact choice of divisors that we want to sum to achieve our n can be any combination, right? So 24 might have more semi-divisors. I'm just making these up. Maybe all of its proper divisors are all of these, but I want to choose some subset. But the subset might include 2, but it also could not include 2. Maybe the subset starts at 4. Maybe it starts at 2. We don't know. So we have to consider every possible possibility. So for each of these, I can choose to take or not take. If I do take, then the general pattern for these type of problems is I'm going to so if I do take my S which is my total, wants to go down, right? So let's say I choose to use, so let's say for a given k, I choose to use it. Then before I was looking to sum up to 24, let's say I have a k is equal to 6, and I choose to bring that 6 into my sum. Then now my new target value n is not 24 anymore. It's going to be 24 minus 6, being 18. And then D is the coin that I'm using. So after every coin I use, I want to move on to the next one, because they tell us that that's cannot contain repeated numbers. And this B here strongly hints that this is going to be the use case. And this is going to be the don't use case. Why? Because if I don't use it, or if I do use it, right? Or so what I noticed is that here I sort of constructed this feasible alphabet of divisors that I can use to comprise my sum, but they don't do that over here, and they do it all in one line. So what that tells me is, rather than producing all the k's at once, we're going to look at one k at a time. And if I choose to use a k, then it must fulfill this condition. So it seems logical to me that the reason I need an extra space here is I need to enforce that divisibility condition. So my parameters are S and D. It seems logical to me that I would want to check that D is able to divide into S. And only if I am able to divide it, then am I allowed to use it. And if I do use it, then C would be S minus K. And then D is going to be the case where I do not use it. If I don't use it, then my sum doesn't change, but I still go on to the next one because I do not want any possible repeats. Is that right? Yep, that's right. Because also if I didn't have a plus one here, then this would simply be infinite recursion. So I know that one of my parameters has to change some. Now we are left to figure out A. So under what case do I immediately know my number is semi-perfect? Well, I know that my S is going to keep going down, down, down. And if it ever hits 0, it seems to me that we should return true, because it means I've been able to find a subset of k's to take away from my sum such that they exactly sum to 0, or equivalently that they successively decrement my S down to 0. So it seems like it would make sense for this to be S is equal to 0. Okay, I'm a bit lucky because what I should have done is I should have looked at this line first, but it just happens that sort of the algorithm I chose aligns with this, but I definitely should have looked here first. It tells us what values are n and 1, or S and D going to start at. So S is going to start at n, and D is going to start at 1. And this makes sense because D, I want to check all of my possible divisors, right? So D should go from 1 all the way up to, like, let's say 23, if my target is 24. And then S is going to start at 24. And then for every given D, I have to check if it is a divisor. So let's say 1 is a divisor. Then I can choose to either, or if it is a divisor, then I'm allowed to include it in my sum. in which case my sum goes down. If I don't choose to include it, then my sum doesn't change, and so forth. Okay. And then basically, if I ever find a combination that goes to 0, then this sequence of k's, this sequence of k's is not only a sequence of divisors because of this condition we're enforcing here, but also, more importantly, that collection of divisors exactly sums up to my s. So I think s of 0 makes sense. N of 0, no, because n doesn't change within the function. S is equal to d. Equal to d. And n is equal to d. Also, the solution probably should not have n in it. Isn't s equal to d also technically correct? Or do they have a doc test for us to help us out? So which of these is it? So each of these just differ by one recursive call. Um, an integer n. So let's think about the simplest case. If s is 0, should that return true? Well, s is an integer. That satisfies it. But 0, you can only piece it together as a sum of zeros. And 0 is not a proper divisor. 0, I wouldn't think. So I actually don't think it should be s is equal to 0, just because if they, oh, well, I think they're saying the input n has to be a positive integer. So 0 isn't even a possible input. So what about 1? Is 1 a semi-perfect number? One is a, yes, 1 is. So if I stepped into this function with n is equal to 1, if I had this base case, it would return true right away, which is expected behavior. If I have um, if I instead have s is equal to 0, well, 1 is not equal to 0, so that is going to force me to go down here into this recursive case. But d is 1. D is 1, you're saying if 1 is greater than would a 1 return false? No, we should be returning true. Um, so I think this base case actually fails for n is equal to 1. Right, because f of 1, 1 should return true, but it would return false because it gets caught by this. Um, let's say, so I'm actually leaning towards this instead. But let's see. So let's say n was greater than 1. Let's say if it's 24 and d starts at 1. D is going to keep going up. Um, so as long as this condition is not true, we just want to keep incrementing d, leaving our sum untouched. But then we find 2, so 24 is going to go down to 22. In that span, d has gone up to 2. And then let's say we find 12. This is going to go down to, or let's say we then find 4, and this is going to go down to 18. Oh, wait. It's going to be 2, 4, 6. The question is, does S ever equal D? Acceleration, I'm going to subtract. So does S ever equal D, or is it the case that one of them lags behind the other? So again, we're going to start at 24, 1. K is going to go up, up until it's 2. And then we enter the frame. This is incorrect. We enter the frame where S is still 24. D is now 2. And we hit this case where 2 is in fact the divisor. Only then do we decrement from the total. And then K is going to go up, up until it's 4. And then only in this state does our S go down to 18. And then D is going to go up, up, up until 6. Only then does this go to 12. And this is going to go up, 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 up to 12. And here I should actually just be able to return true because they're matching. So I think that sort of confirms that that should be the answer. Right, because if they ever match up, I can instantly just return. I think this fail. I actually don't entirely see how this is wrong, but I think it fails for the n is equal to 1 case. I don't know if that's the right justification, but I think both of these make sense, but I'm just gonna sort of rely on gut to go with this and also not to use too much more time. Implement subsums, a generator function that takes a list of unique integers s and a positive integer n. It yields all sublists of s that sum to n, where a sublist is a list containing some of the elements of s in order. Okay, great. So in order is great to hear because that means that I can just iterate through my input list in peace without ever have to worry about consider prior inputs. So this question exactly reduces to yield all subsequences of S that sum to n. Again, this definitely feels like problems we've solved before. This reminds me of that one discussion problem. We had to generate all of the, oh no, I don't think we had a discussion problem to generate all subsequence is a sum to target, but we've had problems where we had to generate all partitions and also return a list of all subsequences that had some like weird increasing condition. Regardless, we've definitely done these style of problems before. Right. And having seen these patterns before, I immediately understand the structure, right? So this structure is going to be include the element, and this is going to be don't include the element. Why do I know that? Because this 4 item in yield, the purpose of this is such that instead of just yielding t, I can yield t plus something, right? And this plus something is going to be the item we include. That is why I need the for loop in the yield. Otherwise, I can just yield from. We have the yield from here because I can just yield from my recursive call without doing anything else because I don't need to include the element. So this is simply a structure that we've seen many times in class. Here we're going to iterate through all of the recursive results. In particular, the result where I decide to include a given item in my list. So as I'm iterating across my list, I can choose to take this one or not choose to take it. And if I do choose to take it, then see. If I do choose to take it, just like last problem, my target sum is going to decrease by the item that I'm now including. If I don't choose to take it, then my sum will not change. And if I do choose to include it, then okay, I better include this item onto the beginning of my yielded value. Otherwise, I will just yield t straight up by using this yield from. And I think this is this regardless, just like last time where we did d plus one regardless. It's because we only want some of the elements in order. Like we notice that here, 1 1 1 1 1 1 1 1 is not a valid sublist. That's because we restrict it so that each item can only be used up once. So therefore, whether I use the item or I don't use the item, on subsequent iterations, this element should no longer be in consideration, which is why we're going to skip it. Also here, if it was just this would infinitely recurse. So let's use what we have to fill out this. Let's do G here. So this is going to be exactly equal to this. No, not this one, this one. So this is going to take everything up to the second or up to the first item and return as a list, exactly what we want. And this is going to be subsums of, we don't use it, the total doesn't change. We have E and F left. F is going to be subsums. And we do choose to include the item, which is why we're going to decrement it from our sum. And once again, we are left with a base case to figure out. So let's do process elimination here. S is a list and N is a number, so this can never be true. This seems to be a little too loose of a base case. Also, can it ever be true? Because S will always be greater than all the elements in N, right? Like N should always be greater than all the items? Or no, N can be equal. So if this was N in S, then let's say we were doing this example, then I would jump into my function. I would say, yep, N is in S. And then I would simply go ahead and yield 12. But 12 is not, oh, 12 is, oh, okay. What about this? N is equal to S of 0. Well, the idea here is that my list is going to keep getting truncated. And if the last item I have remaining is simply what my target is, then I can just yield it. I kind of like this because it matches sort of the philosophy from the last problem, where as my subset or as my alphabet of candidate values or my coins, as it goes down, once it has decreased to the point where the item that I'm partitioning into my sum is equal to the total sum, then yeah, we're good, right? Because I can just return that partitioning piece. Um, so I like this because it aligns with general structure of these problems. And if n is equal to s, um, so if we were to apply that onto this example, we're saying if S ever becomes just a list with 12 in it, then you can return it right away. Hmm. I would say all these are very similar. If anything, I don't actually see the difference between these two. Um, this is very tricky, and I'm really tempted to. I think on the exam, I would skip it and move on. And this also being a one pointer, I would just trust my gut and choose something like this or something and move on. But for the sake of this, I don't want to like have all the timestamps messed up. So I'm gonna try. I'm gonna try to figure this out before I move on to the next part. Still so much left. Okay. Um. So let's construct a simple example. If s is equal to 2 and my target was 2, then what I should be returning is 2. You each of these produce the expected value. Well, if n is 2 and n is equal to s of 0, then yield n. So this does it correctly. If 2 is in 2, then yield n. This does it correctly. If n is equal to s, that does it correctly. Okay. Let's construct a slightly longer example. Is this list strictly increasing? I don't think it has to be. So let's say we had 2, 1. Um, and this should also just produce 2. So this would do the right thing. if n is equal to s of 0, this would do the right thing. And this would not do the right thing because 2 is not equal to 2 of 1. And then this 2 goes away, and then these two can never be equal. So we have eliminated a choice. Um, so instead, let's make this 3. And the expected output should be 1, 2, or 2, 1, and yeah, just 2, 1. So here, n. So here on the first iteration, n is not equal to s of 0, so nothing happens. On the second iteration, I'm going to truncate my list down to 1, and my n is also going to go down to 2, or go to 3 minus 2 being 1. So then we are able to meet this condition and yield a 1. That will produce the 1, which is what we want because we're going to eventually concatenate the 2 onto it. So this looks like it's doing the right thing to me. What about here? I'm going to check if n is in S. N is not in S. So then we get to here, n is now in S, and we yield 1 as expected. So we need more work to figure this out. Again, if I was on the exam, I would definitely skip this problem. I would choose one of these by gut and move on because it's not worth being this stuck on one point. But for the sake of completeness, I do want to get this through. So wait, just make sure I'm recording. I am recording. Fantastic. So I'm trying to construct a case that can differentiate between these two. Um, One potential case I'm thinking of is, can S ever be the empty list? Right. So let's say n is 0, and well, even though this should be true, um, my S is empty, right? So therefore, n couldn't possibly exist in S. But again, we have positive integers. Um, let's see. Let's see how the doc test can help us. So first iteration, we're going to becomes 15, and this becomes 13. This becomes 10, 6. And again, both cases would allow this to successfully yield to 6. But I think, okay. So I think this should be answer. because I think n and s behaves weirdly here, because on the very first iteration, you would say, yes, n is an s. So you would immediately yield a 12, but then you only want to yield 12 once. But by yielding 12, you're allowing subsequent recursive calls to add their own contribution onto the 12. So if we had n is in S, then you would get random sublists that look like this, that occur as a result of this line, right? So you're saying for each of the subsums, you're going to add onto my own contribution to it. And since we've said that 12 is a valid piece, then you're going to have a bunch of people trying to add themselves onto 12, which doesn't make sense. And I got this sort of idea from the fact that this yielded value should always be something that is constrained to happening at the end, right? But I don't want my first iteration to pick up on this and just yield 12 right away. I want this behavior to be constrained to happening towards the end. So I think that's enough justification to go with this. That was tricky, and I hope I'm right, and then restart that time. Yes. Okay. We are in Parsina. Semi-sums takes a positive integer n. It returns a list of all lists of unique proper divisors of n that sum to n. You may call semi-perfect in subsums. Oh God. So we want all proper divisors of n that sum to n. All proper divisors of n that sum to n. How is this different? Okay. So this is a combination of the last two problems, right? So in part A, what do we do? In part A, we return whether it can be semi-perfect or not. In part B, we produce the function that generates all of those sublists that sum to target. So now I'm going to want to go through every possible number. So again, we're going to take the approach where I have a bunch of k's. Each of these k's, I have 1, 2, all the way up to k. I'm going to filter it so that it's only the divisors of n. So maybe that's 4, maybe that's 6, and so on. And then for each of these, we have to ask whether or not I can take a subset of these to sum up to n. And that question simply reduces to finding the subsums, right? So here I'm asking, can I take a subsequence of my numbers to sum up to n? So this ultimately should be a call to subsums, because very conveniently, subsums gives us a list of numbers that sum up to n. And in this case, the n that I want to sum up to is going to be also n. And then here, so subsums takes in an arbitrary list, but here we're going to pass it a very specific list, with that list being the divisors, because those are the candidate values that I want to potentially comprise my sum of. So this is just going to be all of the divisors. Do I care whether or not my divisors are semi-perfect? You may call semi-perfect and subsums. We definitely want subsums, but do I need semi-perfect? Do I need to make sure that my that all of my do I need to make sure that anything in my function is semi-perfect? And this feels weird. It feels tricky because it feels like they're hinting to use it, but I don't think there is anything in my function that says that any piece needs to be semi-perfect. I don't think n needs to be semi-perfect. I don't think the proper divisors need to be semi-perfect. So the only condition I need to check here is divisibility between n and k, not whether or not anything is semi-perfect, I believe. So blank I think is subsums. Blank j, if something. Wow. 3 are calling semi-perfect. They're really telling us that we might want to use semi-perfects. Or I can just check divisibility, which is what I think should be the answer, right? Because the pieces that comprise my sum are simply the proper divisors. I don't think they have to be semi-perfect. So I'm going to go with my gut and save this. I don't think it matters for my n or my k to be semi-perfect. Or what does that mean if my n and k is semi-perfect? If my n is semi-perfect, that means I can compose n as a sum of its proper divisors. Well, okay. So first of all, semi-perfect of n makes no sense because I want something that reacts to k, right? I don't care about n. N is static in every single iteration, so it makes no sense to use n here. Semi-perfect of k, I don't care if my individual divisors are semi-perfect. I just care if my divisor is a divisor. So that is quite rude of them to give you three options like that, but I feel pretty confident it should just be checking for divisibility. For part 4, a function that takes a positive integer n, it returns true if n is semi-perfect. This is so mathy. True if n is semi-perfect and no smaller semi-perfect number is a divisor of n. Your answer should have two expressions separated, comma, good to know. Following filter. Um, so we have to meet two conditions here. If n is semi-perfect and no smaller semi-perfect number is a divisor of n. So they already handled the first for us, so we need to handle the second case right here. And not any map, oh my God. So let's try to go inside out. Not any map semi-perfect onto a iterable. This iterable will be some filtered sequence. Okay, so here seems to be the flow of logic here. I'm going to have some iterable. I'm going to filter it by some condition. And then of this iterable, I'm going to map semi-perfect on it, which will give me like an iterable of true, false, false, true, whatever. And then I say, if not any of them, or let's first start with any. So we're first going to call any on it, right? So this is going to return true if any semi-perfect. But then we want there to be no semi-perfect. So if this is true, then I want to flip that to a false. Whereas if these were all falses as we desire because we want no smaller semi-perfect, then this would all be false. And then if I call any on that, then this would actually be false, which is good for us because we want all falses. Okay, so that's sort of the workflow. And we had to figure out what this very first iterable is. So this is going to handle checking that none of them are semi-perfect. So then it makes sense that here, the only other condition that we have to mandate is divisibility because they handle no smaller semi-perfect. So we have to handle the smaller part and we have to handle the divisibility part. So filter is going to take a function and an iterable. The iterable is how we're going to handle the smaller part, just like we've done before. I'm going to do a range of 1 all the way up to our number n. Guess you could also do list comprehension, although I don't really see a reason why we would want to do that. And then I'm going to filter that range for all the numbers that are divisible by, all right, so let's say for all of the k's in 1 to n, I want to make sure, all right, so I want all of the k's for k in 1 to n if n is divisible by k. So this is going to be the condition that I want to impose on all of my k's. So I'm going to say the function, my filtering function has to be a function, so I'm going to use a lambda. I'm going to say lambda k, which are my divisors, or let's make it d for clarity. If that d is able to divide into my n. Right? So this gives me the divisors. This gives me the smaller. This gives me the fact that they're semi-perfect, and this checks this first condition. We have solved it. How long is this exam? Pretty long. Implement longer, which takes 2 linked lists. It returns the longer of the two. If they have the same length, it returns S. Okay. How do I, given 2 linked lists, how do I return the longer of the two? And I'm sad because we have to do this iteratively, like recursion. So 2 linked lists. This is the longer one, so I will return it. 2 linked lists, they're the same length. If they have the same length, it returns the first one. Okay. So we return the first one. Return the longer and return. Oh, true if they're the same. Wait, why did they return true? Oh, is S.empty. Okay. I think for a lot of previous problems, I sort of had an algorithm and just sort of see if it matched the skeleton. But here I don't really have an immediate idea off the top of my head. I guess if I want to return the longer of the two. First of all, I think I would need sort of dummy pointers that are anchoring the start of my linked lists. Um, okay, so here I would want to return A. I want dummy pointers that point at the beginning because I know that's what I'm eventually going to return, right? And I think. And then how do I iterate through? Actually, I think an algorithm for this would be not too bad, in which we want to just take one single step hops at a time. And the moment that any of them are empty, then I want to quit the loop, and you found the longer one, right? They're saying while B is not linked.empty. What happens if A is linked.empty? I have no clue. Okay. So I think A and B are going to be your anchors. Do you have any multiple choice to help us here? I think either using recursion in here would be kind of funky because we have a while loop. We just have like nested while loops, kind of strange. So if something I can immediately return right away. I would always want to return A's and B's because they're the starts. Those are the anchors at the start. All right, let's go back before we just try to find an answer. Let's go back to refining our algorithm here. So they're checking if B is not linked.empty, right? So if I ever run until the end of B and I hit the end, then that means I should immediately be able to return A because we exhausted B before we exhausted A. But how do I know A is not completely exhausted? So I think D should be return A just because when this loop stops, that means B is empty. So therefore A is longer. I think that's a feasible solution, but I'm not quite sure why we have this if here. While B is not linked.empty. Oh wait, my fault. So A and B are going to be our moving pointers. A and B are going to be moving our pointers, and then S and T should be the ones we return. So no, I do not want to return A. I want to return S, which is going to be anchored to the start. If what should let me immediately return? So considering we're looking at here, we would one of these lines should also definitely be dedicated to looking at A as well. So if A is, what about A? Well, I mean, I guess we also have to check the other case, right? Like if A is empty, then I would return B. Is that the answer? If A is link empty, return B. Right? Okay, so if I don't enter the while loop, that means B is empty, so I could just return A. If I do enter the while loop, that means B is not empty. But then if I check that A is empty, then that means that B is longer. So I think that's what the logic is here. If A is empty, then return T. Else we just step forward. Okay. I think that's it. I think at first it was confusing, but I think it's a rather clean implementation of doing this. It's sort of just achieve the high level idea we were looking at before, right? We're just going to take successive one element hops. If it's ever the case that B runs out, then I know I can immediately return A. I know they can also be equal, but the problem already tells us that they're equal, return the first one. And then the inverse case, if we have this, right? And I'm at this iteration, or I'm at this iteration, and we enter the loop because B is not empty. But now we have to check if A is empty. Well, if A is empty, then B is the longer list. So the final case is we just have to step forward one hop for each. Implement longest, which takes a linked list of positive integers S and a positive integer N, and returns the longest sublist of S with elements that sum to a number less than or equal to N. Do not mutate S. Sorry, I just like zoned out. Takes a linked list of positive integers. The longest sublist of S with elements that sum to a number less than or equal to N. Wow, so many subsequent sum problems on this exam. But here, instead of summing to a target, we're saying you can also sum to a number less than N, and we want the longest one. So to find the longest linked list, it seems like we can use our helpful friend here, longer. Okay. This is recursion. Woohoo. They've done the base case for us. Woohoo. I do not like thinking about base cases. And they return the longer of two things. Then I'll take the longer of two things. So that maps the two possible choices. Um, so given a linked list, well, honestly, this should just sort of align with these same general pattern of taking the item or not taking the item, right? So for a given item, I can choose to include it or not include it. We have our list and we have our n. If we choose to include it, then n will go down. And then, but here the variation is that n doesn't have to hit like exactly 0. Right? So a valid sublist is for any sublist where n is greater than 0, because this means that our sum hasn't reached n yet, therefore sum is less than n, therefore it's a valid sublist. That's actually an interesting twist. Okay, so I mean, these will definitely both be recursive calls. Or no, yeah, so this will be recursive call, and this must be recursive call, just from sheer recursion pattern. I have a general idea of how to do this, but I'm gonna look at the multiple choice for some guidance. So T, they're telling us, has to be the longest of something. S and N is not possible. That's infinite recursion. Um, so D represents the choice of including. I think this, what does that do? So I think it has to be this, right? Because if I choose to include my S dot first, then I have to skip it. Sublist of S. So therefore I can't just keep including a given item forever. Right? So yeah, like here I cannot just include ones forever. So therefore I know that I have to move on to the next item. So this can't be S. And if I move on to the next item, then I've used up that one item. So it should be N minus S dot first. So this is the case where I use. So therefore G must be the case where I don't use, in which case I would want the longest, where I'm still doing S dot rest, but my total doesn't change, right? I'm doing S dot rest here because, again, I don't want to be infinitely recursing, and I do not want to allow the possibility of including the same element multiple times. I need to always be advancing on to the next item for the same reason we did D plus 1, for the same reason we always did S of 1 forward. F, are we just like if T, right? Like I would only want to do this if this returns if this produced a valid list in the first place. Otherwise, it would produce some error. Yeah, so we generally have these ifs to capture like edge cases. And the most obvious edge case if t becomes length.empty. But I mean, I feel like longer should be able to handle that. Because longer knows how to take in length.empty. Yeah. So it would be a waste of space to do if t is not length.empty here. So let's also think about if this were not the case, then I would instantly return t. What would allow me to instantly return t? I mean, I guess the longest, if I choose to include a given element, must be invariably greater than if I had chosen not to include that element, right? Hmm. Hmm. I do wonder how much time I've taken. I wish I kept track of my time. I'm probably at 2 hours soon. What would be wrong with this? Okay, let's recruit more brain cells here. T will be a linked list. Why not? T returns a linked list. So I will produce the longest length if I choose to include the one, which might be like 1, 4. This is what T is going to get bound to. I'm going to take the longer of T, and if I choose not to include the one of just this. And I don't see why. Well, I don't think there's any more in condition we would need to enforce. I mean, my mind jumps to like maybe we have to check some condition between the first two elements, but it's not the case that we want like increasing sublist or something. Um, oh, do we? I mean, mm, we probably need to check. Wait, we need to check that it sums to n or less. Like we're not really using n in this because longer doesn't do that for us. So like if n hits 0 or something. Oh yeah, this is dumb. So I think for the reason I said before, it would be a waste of line to do t is not linked empty. Um, I also don't think it's the case that including it will always produce the longer one because if my first item is like 7, wait, no, if I, hmm, so this is the case where I choose to include s dot first. So like if n minus s dot first is a two pointer. N minus s dot first. is greater than 0. Wait, what? Where in this function are you even constructing a linked list? So my brain is so fried. So I was considering doing the A plus, but I think I'm too tired. Um, Maybe if there's enough demand, I'll try it, but too tired. Where in this function are we constructing a linked list? Like, don't I need links somewhere? Like, I get that I'm going to call longest on it, right? But I need something to actually construct the linked list. No, but this blank is just. Oh, okay. It should be G. We should be doing that in G. Okay, sorry. I'm really not thinking about this problem right now. So I can't like this is wrong because nowhere in my function am I actually chaining together a linked list. So there must be a link here. That's just sort of non-negotiable. So I think T should actually. Oh, okay. It all makes sense. It all makes sense. My fault. Okay. So here's how we have to do this problem. Right. For whatever reason, I sort of assumed that T was the use case, but T cannot possibly be the use case because I do nothing with this T, right? And just calling longest alone cannot possibly produce the longest linked list that includes that first element because that first element has vanished. I'm not chaining that first element onto this result. So therefore, this has to be the don't use case, which must be this because I advanced onto the next item without touching my sum. So now I'm 100% sure G has to be the use case. And why do we need an if? We need to gate this code block with an if because I need to make sure that I'm allowed to use that n. So if n minus s dot first is greater than or equal to 0, only then am I allowed to consider including on that first element. And if I do include that first element, then I need a link because I need to include that first element. So to link on s dot first. And now we're done. Um, I think can this be T? Or no. If we include it, then our sum will go down. Okay. All right. Um, all right. Hope that was helpful. I will review my answers later and summarize.